Today we start our study of machine vision. Machine vision is the study of how to get useful information from a camera. With humans, our vision is the sense we use most extensively to get information about our environment. So if we could figure out how to incorporate vision into our robots, that could potentially get us much farther towards building robots that can effectively perform human functions. The difficulty here is that visual images contain an immense amount of information. On the one hand, that's a benefit because a single relatively easy to get and inexpensive sensor, that is the camera, can do the work of a whole array of other sensors. But there's also a drawback to the immense amount of information. In order to answer relatively simple questions like, is there an object I want to pick up in the view right now? We have to somehow process and sort through this huge amount of information to figure out just the answer we're looking for. Now, the human brain does this impossibly well. In the study of machine vision, we're trying to make our camera code combination work even a fraction as well as the human brain. Keep in mind that machine vision, which is also known as computer vision, is a whole field of study in itself. In this class, we will only be spending 3 days on it. So we'll just be getting started with some of the basic concepts that form the foundation of the field. Machine vision inherently requires the coordination of a camera with code. So the first thing we need to do is learn how to read camera images into a form where we can use them in some programming. To do that, we'll be using a Python library called OpenCV. The CV stands for computer vision, and the open part refers to it being not proprietary. Once you learn how to use OpenCV, you can continue to build your skills and use it in your own robotics projects. We'll start today by installing OpenCV. Go to the URL shown here, and then scroll down and find the place where it says OpenCV Win. Then install the latest version here. Wait until the library has downloaded. After the download is completed, run the executable and click Extract. Wait until the extraction is finished here. After the extraction is finished, go find the file on your computer. It's probably in the Downloads folder. Now find the OpenCV folder and then go to Build, then Python 2.7. Now you have to choose between x86 and x64. If you don't know, you can guess one, and if it's wrong, you'll get an error. So open up the folder and then copy cv2.pyd. Then go find where Python is installed. For me, it's the C drive, then Python 2.7, then library or lib, then scroll down and find the folder called site packages, and then paste the cv2.pyd file here. Now open up Python idle. In the shell, type in import numpy as np. We installed numpy earlier. We just want to always install it first because OpenCV uses numpy. Then type in import cv2 And if you get an error like this, that means you picked the wrong file, either x86 or x64. Go back and get the other one. So I'm going back into my downloads, build Python 2.7, and this time I'm going to take x86, copy it, and then I'll go to where Python is installed, C Python 2.7 lib, and then scroll down to find site packages, and then paste it here and replace the file in the destination. And then we'll go back and try this again. Import CV2. And this time I don't get an error, so we're good to go. Now before we go and write any more code, let's go set up our camera. I'm going to start by cleaning up some of these things that we have plugged in that we're not going to need for the time being. So I'm going to remove the motor and encoder, the potentiometer, and I'm going to unplug the servos that we still have plugged in. And then I'm going to flip this board over and unscrew the screws that are holding the manipulator onto the board. We can very easily put it back on later on when we get to the point where we're going to use the manipulator to pick up objects. For now, I want to use the board as a nice clean surface for my camera to look at. So go ahead and unscrew all 4 of these screws that are holding the manipulator onto the board and just set them aside for the time being. Now the 4 standoffs or offsets will still be attached to the bottom servo, so you can just, after you unscrew these 4 screws, take the manipulator and set it aside for the time being. I'm also going to wipe the board off. We had drawn an X and Y axis here, but for now I want it to be as nice and clean as possible. So wipe off the board, then find this large bracket. This is the bracket we're going to use to attach the camera to the board. If we use this bracket, we'll be able to fix the camera so that it's looking straight down. So just use the little feet of this bracket to clip it to the board as I'm showing you here. Now go get the camera from your kit. The camera looks like this. Open the clip on the bottom of the camera and then use your screwdriver to unscrew this screw that's holding the clip on. Keep track of the screw and the clip because you might want to use it later on. But for now, when you take off this clip, it reveals a little shaft with a couple of flats. That shaft fits right into the bracket like this. Now take the USB cable that's connected to the camera and plug it into your computer, the same computer that you're using to write the Python code. Then we'll start our code with import numpy as np and then import cv2. Now we're going to capture an image from a camera. And to do that, we'll do cap equals cv2.video capture, and then in parentheses here you put a number that indicates which camera you want to capture from. You might have more than one camera connected to your computer. That's okay. Right now, just put in any number here that you want, and later on we'll figure out which number is the correct number. Okay, now we're going to create a while loop. We'll do while 1 so that this while loop will execute forever. And then a colon starts the while loop. Then we need to indent the next line to indicate it's inside the while loop. I'll do underscore comma frame each equals cap dot read open and close parentheses. Cap is the name of our camera that we created a couple of lines ago. The function read reads the next frame coming from the video camera. Frame on the left is the name of the variable that's going to hold that frame that we capture from the camera. The reason we have underscore comma before the frame is because we also need another variable before frame that tells us whether or not the read of the frame was successful. For example, we could do a comma frame, and then the variable a would hold a Boolean that was either true or false, indicating whether we had successfully read a frame. In this case, we don't really care to have that variable that says true or false whether the frame capture was successful. And that's why we're doing underscore comma, just because we're not going to use that variable. Next, I want to show the frame picture in its own window. So we'll put here cv2.imshow and figure 1 in single quotes and then frame. Figure 1 is the name of the image that we'll show, and frame is what is going to be shown in the image. Right now, I have an infinite loop because of the while one. I want a way to be able to get out of this loop. So I'll do k equals cv2 dot wait key 5. This will wait for 5 milliseconds every time we go through the loop to check to see if I've pressed a specific key to get out of the loop. Now, if K, the key that is pressed, is 27, 27 is the code for the escape key, in that case we will break. That means get out of the while loop. Now, I'll do cv2.destroy all windows, and notice that I did not indent this line at all. That's how I indicate that this should not be inside the while loop. Lastly, we need to figure out what number should actually go up here in the capture line. Each camera that is connected to your computer has a number, and the first camera has the number 0. In my computer, I have a front-facing camera, a rear-facing camera, and then I have the webcam from my kit plugged into my computer. So I'm going to guess that the camera that is the webcam from my kit plugged into my computer is going to be number 2. I'll put 2 here, and then we'll run the code and we'll be able to test to see if this is correct or not. After you run the code, a window will pop open showing you the live image from the camera. If you pick the right camera, it should look like this, because this is the picture of the board looking down from the top. If your camera is not in focus, you can turn the little ring right at the camera lens to focus the camera. If the picture that comes up is not from the webcam, try a different number in the line that says cap equals cv2.video capture and so on. You can exit by clicking on this live camera image and pressing the escape key on your keyboard. Now, we are capturing images from the camera and they're being stored in a variable called frame. Let's take a look at what this variable frame looks like. I'll hit the escape key to get out of this loop, and the thing that is printed to the screen here is the contents of frame. It's a big matrix. All of these ellipses, these little dots between the little pieces of matrix, indicate that there are a bunch of more numbers between these little pieces of matrix. I'd like to know how many numbers frame actually contains. So let's type in frame.shape. The numbers shown here say that frame has 480 rows, 640 columns, and 3 layers. Now, let's take a look at the meaning of these numbers. First, notice that the total number of numbers in this matrix is 640 times 480 times 3 equals 921,600. Also, notice that each number in the array is less than or equal to 255. You might recognize the number 255 from our earlier study in analog to digital conversion. This is the largest number that can be represented by 8 bits. In other words, every one of these 921,600 numbers is an 8-bit value. So this whole single image is 921,600 times 8 equals 7,372,800 bits of information. That is a lot of information. If we are going to go through this info and find the answer to whatever individual question we are asking, we need to reduce the amount of information. Now, one way to do this is to change the resolution. We learned previously that the term resolution refers to the smallest change in the input, that is physical property, that a sensor can measure. In cameras, the resolution refers to the number of pixels in the image. The default resolution of your webcam from your kit is 640 by 480, which is 307,000 pixels. Each pixel consists of just one solid color value, and it covers some area of physical space. This is how the resolution of a camera relates to the resolution of a sensor. It is the physical area of space within which we can't detect any changes in color or light intensity. So the 640 by 480 numbers represent the rows and columns of pixels in the image, or numbers in the image matrix. So what does the 3 represent? The 3 represents the color space of the image. Now, you are probably familiar with the RGB, or red, green, blue color space. By combining levels of red, green, and blue, we can reproduce any color. So, our digital image consists of 3 matrices, each of them with 480 rows and 640 columns. In RGB color space, one of the matrices contains all of the information about the red color values, one matrix contains all of the information about the green color values, and a third matrix contains the information about the blue color values. So lastly, what do the actual numbers in the matrix represent? These numbers represent the brightness level. 0 means completely dark, and 255 means completely bright. The number of bits reserved for each of these numbers is referred to as the bit depth of the image. If the brightness values range between 0 and 255, we would say that the image has an 8-bit depth. If the brightness values range between 0 and 1024, we would say that the image has a 10-bit depth. Once we recognize that images are represented in our code as matrices of numbers, we can use this information to process the data to reduce the amount of information to find answers to questions that are useful to us. Let's go back to our Python code and look at an example of accessing color data. We already have a variable called frame that holds a single RGB picture. We want to get the individual parts out of this one matrix representing each of the colors. So in Python, here's how we split one matrix up into several different matrices. We'll create a variable called red, and that will be equal to frame, and then square bracket, colon, that will pull out all of the rows, comma, colon, that will pull out all of the columns, and then 2. Now in OpenCV, when we take a picture that is in the RGB color space, the first layer of the matrix representing the image is actually the blue layer. Then the second layer is the green layer, and the third layer is the red layer. So that's why I've put a 2 here. The first layer is the 0th layer. It's accessed by using 0, and so the third layer is accessed from the number 2. So now we can pull out the green image by doing frame, square brackets, all the rows, all the columns, but only layer 1, that is the layer in the middle, the one between 0 and 2. And finally, we can get the blue part of the image by getting all the rows, all the columns, and just the 0th layer. Now, to test this, let's show all of these images. Actually, I'm going to take all 3 of these, and let's cut them, and let's put them up here before the IM show, and then we can have several IM show lines to show all of the different images we have now. So instead of figure 1, I'm going to call this one RGB. It's the whole color image. Then I'll do another one of these. cv2.imshow. Let's call this figure red. And the thing that we want to show in the figure is the red matrix. And then we'll do 2 more, and I'm just going to copy this line and paste it down here twice. We'll call this one green, and the thing that we want to show here is green, and then blue. All right, click on Run and then Run Module. Let's see what happens. We get a bunch of images opening up here, and you'll notice in the upper left-hand corner of each image, we have a label telling us which image this is. We have an RGB, a blue, a red, and a green. Now, in your kit, find the little set of color shape pieces and pull out the red circle and place it in view of your camera, like this. Let's take a look at what we see. The circle is very bright in the red image, and it's dark in the blue image, and it's dark in the green image. In other words, these red, green, and blue images are showing the grayscale or brightness value of each individual color. Here's the blue circle. When we place the blue circle in the image, the blue is bright and the green and red are darker. The camera has a little bit of confusion between blue and green. Let's try and look at a green object here. Take a green piece and put it into the screen. The green circle is very bright in green and it's much darker in blue and red. In general, red objects are picked up better than green and blue objects, but even so, the green and blue objects are seen as being much brighter in their own color image than in the other color images. Separating an image into its color components is one way to reduce the amount of information in an image and help us to start to find answers to questions that we want to answer, like what objects are in the image and where are they? In the next video, we're going to look at how to find things that change in our image, and we're also going to look at how we might find the actual pixel location of an object in the image. Go ahead and play around with these images and the different color shape pieces that you have, and I'll see you back in the next video.